After speaking with a few of you in the past few days, I realized not everyone knows about SPEC CPU, so I figured I'd give a really quick overview. SPEC is the Standard Performance Evaluation Corporation. It's a non-profit corporation that was established to create standardized benchmarks that are like vendor neutral for the purposes of evaluating performance and energy efficiency of computer systems. So they've been going at it since 1988. That was the first version of SPEC CPU. And they had versions after that in 1992, 95, 2000, 2006, 2017, and now last month, SPEC has released SPEC CPU 2026. There are more benchmarks than just the CPU benchmarks. You probably heard of SPEC JBB. There's also workstation benchmarks and others like for accelerators, data center, and there's got kind of a long tail. We're going to talk about SPEC CPU here specifically. And in particular, I know it may not be the most exciting thing to talk about the benchmark, so I want to talk about the philosophy of how we put this suite together and kind of give you a behind the scenes look at the process and creation. So this is a snapshot of our paper with all the authors. These are the people that are in the SPEC CPU committee. And you'll notice that there are many companies listed here. Let me see if I can get my laser pointer. All right. Yeah. So there's a lot of companies listed here. There's even some on the committee that are not on this list because they're not allowed to publish for their companies. But these folks together, although we are competitors when we use the benchmarks, we come together as cooperators so that we can define the benchmarks, seek measurements on a level playing field across the industry. So we work together to create high quality, portable benchmarks that are drawn from real applications. And let's leave it at that. So a little background about me, like, when I was in grad school, I was using SPEC CPU 2000 and I was always wondering, like, how do they choose these things? I wonder one day if I can be part of that team, right? And I always thought that it was some kind of smoky room where people decide the fate of the world, kind of like the X-Files. It turns out that, there are people behind this, but maybe we are not in a smoky room. We are in a hotel room in Fairfax, Virginia here in 2025. I have this like dazed look on my face right now because we had just gone through 4 days of discussion and we had completed the final benchmark selection at that point. So that's like a year and a half ago. After that, there's a whole process to get it and released. But you see here, folks around here, IBM, Oracle, Apple, Intel is here, the NVIDIA, here's like the AMD corner, ARM on the back row are people from the IEIT in China, and off the picture are like Dell and HP. Those are the folks. On the back wall, you'll notice self-similarity plots of basic block vector diagrams of all the candidate benchmarks. And so we had about like 27 here on integer on the left and maybe 27 on the right for floating point. And from those, we ended up choosing about 14 on each side. But yeah, we were really stuck in this hotel for 5 days because there was a snowstorm that came through. So we became very good friends also. So this is February 2025, but before that, there's a long process where we had a benchathon where we all got together and in person worked on benchmarks together. And we've had meetings, multiple meetings every week for the last 4 years to do the development. So you can see people here hard at work, except maybe this weirdo. So the goal here, the goal is to develop benchmarks from real applications and adapt them. So many people like to make their own benchmarks now for their specific domain. We can take lessons from SPEC as we do this because SPEC has kind of put these values in stone as the pillars of what they do. Benchmarks should be able to run and produce results in a deterministic and reproducible manner, and they should be verifiable within some tolerance. I like to say we can run something very quickly and get the wrong answer, but that's not a good way to measure performance. So we have to get the right answer. We keep them ISO standard and portable, and that's really key. The reason why people still use SPEC CPU 2000 a quarter century later is because it was adapted to be ISO standard code. So that's why it can still build and run. We strive to do that for every release version so that it can be run backward and forward compatible with any ISO compiler. We're running cross-platform on like 7 or 8 different ISAs, compiler versions, operating systems, Windows. That's really tough. But that digs up a lot of bugs for portability's sake. We're using contemporary code bases. This is now code that's like C++17, uses some of the newer standard templates and so forth. And we try to seek applications that are diverse and non-overlapping in their domains. So they exude a different kind of microarchitectural behavior. They're not all the same, and they come from different domains in the industry. So we have a process for how to kind of ingest candidate benchmarks. One of the things that we do is we go through a search program, and we announced this, I think, in 2020 for this version of SPEC CPU. This is a great way to engage the community. We kind of have like a 4-step process where we do the development. We put it on Rails, offer monetary rewards and stipends. And this is one way to get people to contribute. And so what I want to share now is like how we solicited entries from the GitHub community, GitLab community, open source. So one example is JSBSim. This is a flight dynamics model, and I have just pasted my approach on their community at their GitHub. So the things that you do, like you say something nice about their community and how it's like a longevity of work that you've done. JSBSim is actually a flight dynamics model used in like NASA and Boeing flight simulators, and it's used in the Unreal Engine if you're a gamer. I approached them and asked them if they can help. I lied about how much work there's left to do. I said, hey, I've done 90% of the porting process to putting into the harness. This was in 2023, and I was young and naive and didn't realize there's another 90% to do after that. And so this GitHub issue actually has 200 comments where we're going back and forth and discussing all the problems that arose in portability. We found bugs that we had to dig up into a 1971 astrodynamics textbook. And it was really cool. So the community was like super responsive, very helpful, and we really had a good collaboration there. And so JSBSim turned into 748 Flight DM in the FP suite. Here's another one. This is OpenColor.io. It's a color management pipeline for visual effects. And so I approached them. I tried to relate to the community and said, hey, I'm a filmmaker. And more importantly, I asked qualified questions, right? So if you go in and learn a little bit about what they do, and I don't know everything about VFX, but I can talk about LUTs and tetrahedral color conversion. And so they did not submit an entry into the search program. However, they said, we can help you craft workloads. And that's really important because they were able to give us the benchmark that they use internally for everything that they do. And so that was really helpful. By the way, OCIO is the only SPEC CPU benchmark to have won an Oscar. There's a video about that at the Academy. Here's an example about Heis. Heis is a linear programmer solver. We reached out to them because we had problems with how to verify. And the thing about linear programming is that I have a really quick kind of description here of how solvers work, and they tend to be this like iterative thing where like you kind of start here and you're trying to find some solution like over here, and then you kind of iterate around this thing. And what we were seeing was that depending on the system that you're on and how much floating point optimization you do, you could actually take like a shorter path to here, and now you've violated the equal work principle. So if you're doing less work and you're 5x faster, maybe that's not a good comparison either. Now, what'll blow your mind is that this shorter pathway on the green was actually done with a O2 build, while the red one is O fast build. So that doesn't make sense. It turns out that we couldn't solve this problem, and we ended up voting this one out. So I want to just share like the benefits of community supported development include this kind of expertise is at your fingertips. If people are really engaged, then you can solve these problems. And actually, we can't all be workload experts, but if you bring the experts to you, then you know that you're building something that has value for multiple people and for the whole industry. The process is totally open and transparent. We're doing this on these, GitLab, GitHub, SourceForge, and so forth. We're getting qualified inputs, right? This is not me trying to make synthetic workloads on something I don't know. We're actually getting something real. And importantly, when you do this with people, then you share a journey and everybody's enthusiastic. And there is some evidence of the enthusiasm. Uh, we have NS3, Gabriel in Brazil. This is a network simulator. This is a brain simulation model called Nest. We have Vlad over here in NYC. I sent him a shirt and he liked it so much that he made one for his kid. So maybe he's the real next generation. Amir and Amin over there in Toronto, we're working on VPR for us. And then, of course, like our friends at UT Austin helped provide like dendrogram analysis. And so that shows that we can work together. A lot of people ask like, hey, like what kind of criteria led to applications being excluded? And so this is really important. We talked about the non-determinism in highs. That was one really good example. Sometimes we have a lot of applications that are in the same domain. So we had like 4 different applications that are doing data compression, and we ended up choosing one of them because they all kind of look the same. If you have a really old code base, one of the applications that was offered was the NASA parallel benchmarks. Well, those were written in 1991, and we want something a little bit more mature than that. So those kind of got downvoted. Development divergence. This is something really important. A lot of people ask like, hey, where are the AI workloads? What kind of new benchmarks do you have? And the story I'll give is like we had looked at Llama CPP and Whisper CPP. Those are great inference benchmarks that run on CPU. When you dissect Llama CPP and you turn off processor-specific code and the assembly language intrinsics, then you're basically left with this tight for loop that's doing the matrix multiply. And that changes the characteristic of Llama in such a way that it's no longer memory bound. It's doing inefficient CPU computation kind of slowly, and it no longer represents what people run in the field. And the divergence is so large that nobody on the committee thought it was a good idea to move forward with that. And so a lot of these workloads like media codecs have that problem. Cryptography has that problem. And of course, like some of the newer AI has that problem. We do have a couple AI workloads that do neural network inference in kind of the classical way. We have Stockfish and there's Marion that does machine translation. The other two here, if you have too much IO or you're only running in like one small function, that's maybe not interesting. So we get rid of that. And if there's any bias that is seen by committee members, then that also is kind of evicted there. So after that, what's left? We are left with candidates that are deterministic, reproducible, portable, cross-platform, and all the wonderful things that we spoke about. So that's how we choose benchmarks. One thing I want to talk about is not only were we able to expand the set of benchmarks and adapt them to be kind of solid under the umbrella of SPEC CPU, but we proposed a new way to run in a heterogeneous way. And we started this around the time that this movie came out called RRR, that was 2022. So our heterogeneous run method is called rolling round robin. So rolling round robin is motivated by the fact that the normal spec rate is running the same benchmark on all the cores at the same time. And we wanted something a little different. So I'm going to throw this up here. I was talking to some people about this at lunch. Many years ago, a brigade of soldiers marched in military step across a bridge in England, and their steps hit a resonant frequency and the bridge was then broken apart. And this metaphor explains how homogeneous ref rate exercises many core machines in kind of the worst case scenario. And it exposes a lot of corner cases, but modern server systems, like when you run top on your compute server, you have so many things running. And we want to also showcase like a multi-tenant variant of like how you can run these hardened benchmarks. So what we have here, this is the traditional ref rate. You have time on the bottom and kind of copy count, or you can call it core count along the side. And you're running 48 copies of Stockfish, followed by 48 copies of SQLite. And this is just the normal way to run things. You could take all of those chips there, kind of throw them up and organize them in a different way so that now you have a heterogeneous workload. And the heterogeneous workload, you are still doing the exact same work between the right side and the left side. On the right side, each core at any given point in time is affected by noisy neighbors and could be impacting because it is a noisy neighbor. It starts to expose these kind of things. The cool thing is that this is reproducible and deterministic. when you run it on the same system, you run this multiple times, because the schedule is fixed, you can still get the same answer as many times as you run. And the variance between the different chips there on one benchmark, you get a kind of a shmoo. That's also deterministic. So the variance doesn't vary. So now this is a way that you can measure variance in a deterministic way across your CPUs. And what it leads to, let me just share. This is a way that we can standardize multi-program load. A few years ago, people were trying to figure out, like, how do we pair programs together and test them out? And there's a lot of literature on this, and everybody was doing them in different ways. And now we're offering a way where you can do it the spec way, and it's kind of been blessed and debugged. And now you can compare between your research. So this is deterministic and reproducible on the same system. We have some trouble across systems. Here's where there's an open call for research. How would you compare like a system that has a slightly different interaction because its cores are different? So that's kind of open. But we're trying to address and model realistic contention, expose noisy neighbors, and then enable new research. So what this is going to allow you to do is, like, if you're an operating systems researcher and want to try to figure out how to schedule a heterogeneous load, you can try it out using this and not be succumbed to weird IO or network issues and stuff. This is purely CPU centric. So that's rolling around robin. I'll end with the learnings to keep with you here. The main thing is we developed this in an open and transparent way. I think that's crucial in getting the community involved to help do benchmark curation and creation. We're turning modern applications and adapting them into benchmarks. These are real applications, they're not synthetic. And we hope that these can represent a small slice of what's running in the field. We didn't talk about this in this talk, but we do have a wide variety of UART behaviors. We tried to pull it more towards the front end bottleneck side of our CPUs. There's a lot more code heavy benchmarks, ITLB misses and so forth. We have introduced heterogeneous schedule. And for the first time ever, the pricing for academics is 0. So you can sign up at the SPEC website and download this and try it out. And that's all we have.
So I have one question. I mean, about what you expect about other results. So first of all, why benchmark now? I understand it's exciting to be in the cigar room, but like, why do we really need another benchmark, right? And
let's do that one first.
Okay.
So it's not a new benchmark. It is an existing one that's been around for 40 years. And the most important part is the pillars and the values that we have of making it CPU centric and reproducible and validated and stuff. There's a lot of benchmarks that don't do validation. I can name some of them, right? But I'm not going to besmirch them, right? So I think that's probably the most important thing, is that we're continuing this lineage.
So the second part is like the future. When do you think we need another one? And think like this methodology is sufficient enough for us, or like we need to constantly change this benchmark, deploy it, and benchmark. Basically, I'm trying to get it to the point that like maybe we need a committee that constantly review and receive suggestion and add or remove benchmark or so on.
Yeah, it's a good idea to have a committee. Good thing we have one. It's the SPEC CPU committee, and you are all welcome to join. The people in that room there, we are on the committee, but that group changes. A lot of those people have retired already, and that is leaving room for the next generation. So that's, what I want to share here is this paper is a template for how to create this kind of thing. Whether you do it for CPUs or some other domain, we show you how you can do it. And the next generation really refers to the next set of stewards who want to take this somewhere else, right? So it is in our hands here.
Yeah, so great work. You put deterministic and reproducible in the same category. I don't think they quite belong in the same category. I think there are a lot of non-deterministic phenomena
Yes.
that can be added to the PSS.
Yep.
So does your exclusion of non-deterministic workloads wholesale bias spec from excluding entire areas of workload from the
Yeah, the question was about exclusion of workloads that are things like the linear solver that I mentioned, right? So we do have some constraint solvers that we have put in. And the way that we got around this problem was really novel. I don't know. We realized that we could offer a program, an input that is unsatisfiable. And so if you offer that, then you know that every single system will have to go through and look at all the nodes and search the entire space to determine that, oh, it is unsatisfiable. So the work is equal at that point, right? As long as that problem still represents that domain, it's still valid and it fits under the umbrella of specs pillars.
I guess I didn't quite get this one in RRR. You have non-determinate and you accepted that. And you
Right.
And then for an individual workload, you dismiss it as a problem.
We start with individual benchmarks. Yep. And we move on from there. So the thing about RR is that this is a exhibition sport in spec CPU. So you can make a score out of the normal spec rate, but the committee does not yet let you make a score out of RR. You'll get all the times and all the data and everything there and the variance. You can run it, but the jury's out right now on how to actually score this so that you can compare systems. So that's open research that we invite people to come and contribute for. Yeah.
Thank you, Mahesh. Yeah.
Thank you.
Thank you.
One thing I'll share is like, please cite our paper. And I know might be pandering, but a lot of you cite www.spec.org/CPU 2017, and that's not a citation, that's a URL. There's actually a paper for 2017. There's a paper for 2006 as well, but nobody cites it. And I know they look at these things, they're like,